Hey, I've been reading up on superconductors lately, and it's incredible how these materials can conduct electricity without any resistance when cooled to a critical temperature. Did you know this phenomenon was first discovered by Dutch physicist Henk Kamerlingh Onnes in 1911?
Absolutely fascinating, isn't it? Onnes observed that mercury exhibited zero electrical resistance at temperatures close to absolute zero. Since then, superconductors have been a subject of intense research due to their potential applications in various fields including electronics, medicine, and power transmission.
To really grasp how superconductors work, you have to understand the concepts of electrical resistance, electron pairing, and quantum mechanics. Normally, electrical resistance in materials arises from the scattering of electrons by atoms, impurities, or defects. This scattering dissipates energy as heat, which is why materials like copper or aluminum heat up when current flows through them.
Exactly. In superconductors, however, this scattering doesn't occur below a certain temperature, allowing for the unimpeded flow of electrical current. The key to this lies in the formation of Cooper pairs. These are pairs of electrons that move through the lattice structure of a superconductor in a correlated manner. In a conventional conductor, electrons behave as individual particles and get scattered. But in a superconductor, electrons pair up due to attractive interactions mediated by lattice vibrations called phonons.
That's right. This pairing mechanism is explained by the Bardeen-Cooper-Schrieffer theory, or BCS theory, formulated in 1957 by John Bardeen, Leon Cooper, and Robert Schrieffer. Cooper pairs behave as composite bosons, allowing them to occupy the same quantum state. This collective behavior enables them to move through the lattice without scattering, which is the basis of zero electrical resistance.
When the temperature of a superconductor is lowered below its critical temperature, Cooper pairs form and condense into a single quantum state, creating a macroscopic quantum phenomenon known as the superconducting state. Another fundamental aspect of superconductors is the Meissner effect, discovered by Walter Meissner and Robert Ochsenfeld in 1933. The Meissner effect describes the expulsion of magnetic fields from the interior of a superconductor when it transitions into the superconducting state.
Unlike perfect conductors, which can exclude magnetic fields through induced currents, superconductors actively expel magnetic fields due to their intrinsic properties. This occurs because the superconductor generates surface currents that create a magnetic field exactly opposing the external field, resulting in its cancellation within the material. This is essential for the stability of superconductivity, as it ensures the superconducting state is maintained in the presence of external magnetic fields.
However, the Meissner effect is not absolute. Superconductors can only sustain magnetic fields up to a certain strength known as the critical field. If the external magnetic field exceeds this critical value, the superconducting state breaks down, and the material reverts to its normal resistive state. Superconductors are classified into two main types, Type I and Type I.
Type I superconductors, like lead and mercury, exhibit a complete Meissner effect and transition abruptly from the normal to the superconducting state at their critical temperature. They have low critical magnetic fields, making them unsuitable for applications requiring strong magnetic fields. Type I superconductors, such as niobium titanium, and high-temperature superconductors like yttrium barium copper oxide, behave differently.
Indeed, Type I superconductors have two critical magnetic fields, the lower critical field and the upper critical field. Between these two values, the superconductor allows partial penetration of magnetic fields in the form of quantized vortices while still maintaining zero resistance. This mixed state, or vortex state, is unique to Type I superconductors and enables them to operate in much higher magnetic fields compared to Type I superconductors.
High-temperature superconductors, discovered in the 1980s, have critical temperatures significantly higher than conventional superconductors. These materials, often based on copper oxides or iron pnictides, exhibit superconductivity at temperatures above the boiling point of liquid nitrogen, making them more practical for applications. However, the mechanisms behind high-temperature superconductivity are not fully understood and remain an active area of research.
Superconductors have numerous potential applications due to their unique properties. One of the most promising areas is in power transmission. Superconducting cables can carry much higher currents than conventional cables with virtually no energy loss, which could significantly improve the efficiency of power grids. Additionally, superconductors can be used to create powerful electromagnets for applications in magnetic resonance imaging MRI machines, particle accelerators, and maglev trains.
These superconducting electromagnets generate strong magnetic fields without the heat dissipation problems associated with conventional electromagnets. Another significant application of superconductors is in quantum computing. Superconducting qubits, the basic units of quantum computers, exploit the quantum coherence properties of superconductors to perform calculations at speeds far beyond the capabilities of classical computers. Quantum computers have the potential to revolutionize fields such as cryptography, materials science, and complex system simulations.
Despite their potential, superconductors face several challenges for widespread adoption. One primary obstacle is the need for extremely low operating temperatures. While high-temperature superconductors operate at higher temperatures than their low-temperature counterparts, they still require cooling to cryogenic temperatures, which can be costly and technically challenging. Advances in materials science and cryogenics are essential to make superconducting technologies more practical and economically viable.
Another challenge is the brittleness and fabrication difficulties of many high-temperature superconductors. These materials often require complex manufacturing processes and can be difficult to form into wires or other useful shapes. Research is ongoing to develop more flexible and easier to fabricate superconducting materials, as well as methods to integrate them into existing infrastructure.
In summary, superconductors represent a remarkable state of matter characterized by zero electrical resistance and the expulsion of magnetic fields. The core principles of superconductors involve the formation of Cooper pairs, which move through the lattice without scattering, and the Meissner effect, which expels magnetic fields from the superconducting material. There are two main types of superconductors, type I and type II, with high-temperature superconductors offering the promise of more practical applications.
While there are significant challenges to overcome, the potential applications of superconductors in power transmission, medical imaging, transportation, and quantum computing highlight their transformative potential in various fields. As research continues, superconductors may play an increasingly important role in advancing technology and improving efficiency in numerous applications. It's an exciting time for this field, with many possibilities for innovation and discovery.
Absolutely. The more we understand about the fundamental properties and behaviors of superconductors, the better equipped we'll be to harness their full potential. Continued interdisciplinary research, combining insights from physics, materials science, and engineering, will be crucial in overcoming the current challenges and pushing the boundaries of what's possible with superconducting technology.
And as we explore new materials and refine our techniques, we might also discover entirely new phenomena that could open up even more applications. The field of superconductivity has already revolutionized our understanding of electrical conduction, and it holds promise for many more breakthroughs in the future.
Indeed, it's amazing to think about how far we've come since Heike Kamerlingh Onnes first discovered superconductivity over a century ago. His work laid the foundation for an entire field of study that continues to grow and evolve. Each discovery builds on the last, bringing us closer to realizing the full potential of superconductors.
Speaking of building on past discoveries, the development of type II superconductors and high-temperature superconductors really showcased how iterative and cumulative scientific progress can be. Each new material and each new theory add layers of understanding, allowing us to design better experiments and develop more effective applications.
Exactly. And with modern computational tools and advanced experimental techniques, we're now able to investigate superconducting materials at a level of detail that would have been unimaginable just a few decades ago. This precision helps us identify the specific conditions and mechanisms that lead to superconductivity, paving the way for targeted innovations.
Moreover, the interdisciplinary nature of superconductivity research means that advancements in one area can have ripple effects across multiple fields. For instance, improvements in cryogenic technology not only benefit superconductors but also have implications for other areas like space exploration and medical imaging.
That's a great point. The synergy between different scientific disciplines often accelerates progress. And as we continue to push the boundaries of what's possible with superconductors, we're likely to see a range of new technologies emerge that can tackle some of the world's most pressing challenges, from energy efficiency to quantum computing.
One particularly exciting prospect is the potential for superconductors to revolutionize our power grids. By reducing energy losses in transmission and enabling more efficient energy storage, superconductors could help create a more sustainable and resilient energy infrastructure.
And in the realm of medicine, superconductors are already making a significant impact through MRI technology. As we continue to refine these materials and their applications, we could see even more advanced diagnostic tools and treatment options emerge, improving healthcare outcomes around the world.
It's clear that the potential of superconductors is vast, but to fully realize this potential, we need to continue investing in research and development, fostering collaboration between scientists, engineers, and industry leaders. Only through sustained effort and innovation will we be able to overcome the current challenges and unlock the full benefits of superconducting technology.
Agreed. It's a challenging but incredibly rewarding field. The work we do today builds the foundation for the technological advancements of tomorrow. The promise of superconductors is not just in their scientific intrigue, but in their potential to transform our world in practical and profound ways.
And it's encouraging to see so many young researchers and new interdisciplinary projects emerging in the field. Their fresh perspectives and innovative approaches will undoubtedly drive further breakthroughs.
Definitely. The enthusiasm and creativity of the new generation of scientists are crucial. They bring new ideas and energy to the table, which is essential for tackling the complex problems we face with superconductors.
I think it's also worth mentioning the importance of public and private sector support for research. Sustained funding and investment in superconductivity research are vital for maintaining momentum and translating scientific discoveries into real-world applications.
Absolutely. Collaboration between academia, industry, and government can accelerate the development and deployment of superconducting technologies. By working together, we can overcome the technical and economic barriers more effectively.
It's an exciting journey, and we're only just scratching the surface of what's possible. The future of superconductors is bright, with endless possibilities waiting to be explored and harnessed for the betterment of society.
Cheers to that. Let's keep pushing the boundaries and working towards a future where the full potential of superconductors is realized, benefiting generations to come.
As they wrap up their conversation, they reflect on the remarkable progress made in the field of superconductivity and the exciting prospects that lie ahead. The journey from Heike Kamerlingh Onnes's early discoveries to the advanced research and applications of today underscores the power of scientific inquiry and collaboration. With continued dedication and innovation, superconductors hold the promise of transforming various aspects of modern life, from energy efficiency and medical imaging to quantum computing and beyond. The future is indeed bright for this extraordinary field, and the possibilities are as boundless as the curiosity and creativity driving it forward.